Hello students, welcome to aimsindia online classes. This is a chemistry session. In this we are discussing about the chapter atomic structure. In this session we are going to say about Bohr's model of atom. In 1913, one of the Rutherford's students, Niels Bohr, proposed a model of atom that was consistent with Rutherford's model of atom as well as the quantum theory of radiation. So based upon these two, by consisting these two philosophies, Rutherford's model as well as quantum theory of radiation, Niels Bohr in 1913 proposed a model which is called as Bohr's model of atom. He modified the problems and limitations associated with Rutherford's model of atom. So, as we have seen in the earlier classes, even though Rutherford has given much clarity about the structure of the atom, there are some limitations or some drawbacks in the Rutherford's model of atom. There are some questions where Rutherford could not give answer regarding the structure of the atom. So, Niels Bohr modified his theory and given answers for those questions, rectified those problems which are there in the Rutherford's model of atom. Let us see here the important postulates of Rutherford Bohr's model of atom. That is, first one is electrons revolve around the nucleus with a definite energy in concentric circular orbits, which are called as orbits or shells. These orbits are denoted with the symbols K, L, M, N, and so on. Or these are given numbers 1, 2, 3, 4, and so on. Okay, electrons are revolving around the nucleus in an atom in concentric circular paths, concentric circular imaginary paths. These imaginary paths are called orbits or shells. So this point was there in Rutherford's theory also. Just let us recollect once. Now these orbits are denoted with the symbols K, L, M, N, and so on. So the shell which is nearest to the nucleus is denoted with the symbol K, and next to that L, and next M, and next N, and then O. In this way, denotations are given for the orbits in an atom, and the same orbits are given the numbers also. The orbit which is nearest or closest to the nucleus is given number 1, and next one 2, and third one, fourth one. In this way, numbers are also given for these shells. Now we can say first shell means K shell, third shell means M shell. In that way, the denotations are given for these shells. The electrons have the least energy in the K shell of an atom, followed by L shell, M shell, and N shell, etc. So the electrons present in the first shell, which is very nearest to the nucleus, there the electrons present in that shell are having least energy. And then the electrons present in the L shell, and then M shell, and then N shell. In this way, as electrons are being very close to the nucleus, they will be having less energy. As the distance between the orbit and the nucleus increases, the energy of the electrons in that orbit will increase. So electrons which are nearest to the nucleus are having lowest energy, and the electron which is farthest to the nucleus are having greatest energy. Okay, energy of the electron increases as the distance between the nucleus and the orbit increases. Okay, as long as an electron revolving in the same circular orbit, the energy neither radiated nor absorbed by the electron. So whenever an electron revolving in a particular orbit around the nucleus, it will be revolving with the continuously the constant energy that won't radiate energy nor absorb energy. That is why these orbits are specially called as stationary orbits or stationary shells. Why? Because as long as an electron revolving in an orbit or shell, it neither gain energy nor lose energy. It will be the constant energy always until and unless it changes its orbit. If it is in a particular orbit, its energy will be fixed. That is why these orbits are called stationary orbits or stationary shells. But energy of the electron changes only when it moves from one orbit to another orbit. Until and unless it moves from one orbit to another orbit, its energy will be fixed. It won't radiate energy or it won't absorb energy. That's why you said these orbits are called stationary orbits. But when electron jumps from or moves from one orbit to another orbit, it changes its energy. Energy is absorbed by the electron when it jumps from inner orbit to higher orbit, because as we told, inner orbits will be having lower energy, or the electrons present in the inner orbit will be having lower energy, and the electrons in the higher orbit will be having greater energy. So when an electron jumps from lower orbit to higher orbit, so to be in the higher orbit, it should have great energy. So when electron jumps from lower orbit to higher orbit, it absorbs energy from the surroundings. But when electron jumps from higher orbit to lower orbit, then it radiates energy. So these two are vice versa. When electron jumps from lower orbit to higher orbit, it absorbs energy. When an electron jumps from higher orbit to lower orbit, it emits energy or it radiates energy. This energy changes during the electron jumps from one orbit to another orbit is given by the formula delta E, that is energy change. We are telling here when electron jumps from lower orbit to higher orbit, that electron will absorb energy. If electron jumps from higher orbit to lower orbit, that electron will release or radiate energy. That amount of energy released or absorbed will be the difference in the energies of the electron in those two orbits. It is mathematically given by the formula delta E is equal to E2 minus E1, that is equal to h nu, where E2 and E1 are the energies of higher orbit and lower orbit respectively. So if an electron is jumping from lower orbit E1 to higher orbit E2, then that electron will absorb an energy which is equal to delta E, which is equal to the difference in the energies of the electrons in the two orbits E2 and E1, which is also equal to h nu, where h is a Planck's constant and nu is the frequency of that radiation either emitted or absorbed. Okay, this is according to Planck's quantum theory. That's why it is told at the starting. This Bohr's theory is consistent with Rutherford's model as well as Planck's quantum theory of radiation. So here the energy emitted or absorbed by the electrons while jumping from one orbit to other orbits is consistent with Planck's quantum theory. That is, energy is directly proportional to frequency, or energy is equal to h nu. So here the energy absorbed or emitted is equal to h nu. That is given by taking the difference between those two energy levels. That is E2 minus E1. Okay. Next, defects in this Bohr's model of atom. Even though it is giving much clarity about the structure of the atom, how electrons are existing in the atoms, where electrons are revolving around the nucleus, why those orbits are called stationary orbits, how energy changes occurs when electron jumping from one orbit to another orbit. So these all are given. Even though it is giving much clarity about the structure of the atom, there are some drawbacks or limitations even in this Bohr's model of atom also. Let us see those. One among them is Bohr's theory could not explain the atomic spectra of higher elements such as helium, lithium, beryllium, boron, carbon, etc., which have more than one electron. That means Bohr's model of atom is restricted or limited, or it is applied only for only for the single electron species. This theory is not applicable, or this theory could not explain the atomic spectra of atoms with more than one electron. It is applicable for only single electron species like hydrogen or hydrogen like ions, which are containing single electron. This is a major drawback or limitation of Bohr's model of atom. And Bohr's model could not explain even hydrogen spectrum obtained using high resolution spectroscopes. Actually, Bohr's theory explained hydrogen spectrum. Hydrogen spectrum means he studied and given the model of atom by observing hydrogen atoms. He studied the energy emissions from hydrogen atoms. He observed that when electrons are jumping or given energy, they jump into higher energy levels in the hydrogen atoms and they jump back to their first orbit. So they release energy. He made this energy to fall on the screen. Then he observed some lines on the spectrum. There are some lines on the screen. He called these lines as spectrum. So this spectrum is obtained from the hydrogen atoms. So he called them as hydrogen spectrum. So in hydrogen spectrum, there are different lines on the screen. So this is because electrons are jumping from higher orbits to lower orbit. So they're emitting energy. This he called as hydrogen spectrum. Till there, he explained. But if you observe this hydrogen spectrum by using high resolution spectroscopes, this each line again consists of two or more closely spaced lines. So why these each line again having the different lines inside? For this question, Bohr could not give energy explanation. He explained according to Planck's quantum theory, energy emitted by the atoms or electrons is being in the small packets form. It is not being continuous. So it is being in the form of small packets which are called as quanta. According to this, he observed some lines in the hydrogen spectrum. These lines are because this energy emitted in the small packets form instead of continuous form. So there are some lines with dark backgrounds. This was explained by Niels Bohr. But later to him, the same observed through some high resolution spectroscopes. There they have observed scientists is lines in the hydrogen spectrum still they consist of two or more closely spaced lines. Why these lines are there in the hydrogen spectrum? For this, Niels Bohr could not give any answer. So, Bohr's theory kept with this limitation. One more, it could not explain the Zeeman effect, which was not observed by Niels Bohr. That is, in the presence of magnetic field, each spectral line is splitting into different number of fine lines. This phenomenon of splitting of spectral lines in the presence of magnetic field is called Zeeman effect. Why these lines in the hydrogen spectrum are splitting into fine lines in the presence of magnetic field was not explained by Niels Bohr. That's why you say Zeeman effect. Bohr's theory could not explain Zeeman effect. What is Zeeman effect here? That's a splitting of spectral lines in the presence of magnetic field. So Zeeman effect was not explained by Bohr's theory. One more in a similar way, when these spectral lines are influenced by electric field, then also they're splitting into different fine lines. That is called Stark effect. So Bohr's theory could not explain Zeeman effect as well as Stark effect. What is the Stark effect here? The splitting of spectral lines in the presence of electric field is called Stark effect. So Bohr's theory could not explain these two effects, Zeeman effect and Stark effect. That is a splitting of spectral lines in the presence of magnetic field as well as in the electric field. One more drawback is Bohr's theory could not account for the formation of chemical bonds. That means he could not explain why elements are participating in the chemical bond formation. Why the elements are forming different compounds. Why some elements are not participating. So for this, how these elements are participating in the chemical bond formation was not explained by Niels Bohr. So he could not account for the formation of chemical bonds. Okay. These are the major drawbacks in the Bohr's model of atom. Now let us say about distribution of electrons in the orbits. How electrons are distributed in the orbits. Niels Bohr told that electrons are revolving around the nucleus in the specified imaginary paths around the nucleus, which are called as orbits or shells. Now, how these electrons are distributed in these orbits? There are so many orbits like K, L, M, N and so on. How the electrons of an atom are distributed in these orbits? Let us see here that. This systematic arrangement of electrons in different shells or orbits of an atom is called electronic configuration of that element. So, the systematic arrangement for every element, electrons are arranged in a systematic way. This systematic arrangement of electrons in the orbits of an atom is called electronic configuration of that element. For writing the electronic configuration of an atom, we should know certain points. They are the total number of electrons present in the atom. So first we have to know how many electrons are there in that atom so that we can understand how these electrons are arranged later. So how can we know the number of electrons present in the atom? Based upon its atomic number. If we know the atomic number of an atom, we can say its number of electrons, because atomic number is equal to the number of protons present in the nucleus. And for a neutral atom, it is also equal to number of electrons. So if we know the atomic number of an element, we can say the number of electrons or the total number of electrons present in the atom. Next we have to know the maximum number of electrons that can be accommodated in each shell of the atom. We are telling there are so many number of shells in an atom. The number of shells in an atom is infinity, even though it has 1 electron or 100 electrons. So how these electrons are accommodated in each shell? What is the maximum capacity of each shell? If you know these two, total number of electrons present and the maximum number of electrons that can be accommodated in each shell, if you know these two, we can try to write the electronic configuration of elements or the arrangement of electrons we can understand. So for that, Bohr and Bury scientists together proposed certain rules for better understanding the electronic configurations of atoms. So they have done some studies on this arrangement of electrons in the atoms. So far they have given certain rules for better understanding the electronic configurations of the atoms. Let us see those rules here. First one is the maximum number of electrons that can be accommodated in a shell is given by the formula 2n square, where n is the number of shell. According to, so here the maximum number of electrons that can be accommodated in an orbit is given by the formula 2n square. Here that n represents number of that shell. Let us see here, according to this formula, maximum number of electrons that can be accommodated in the first shell means n is equal to 1. So in the formula 2n square, if we substitute n place 1, what we get? 2 into 1 square, that is 2. So maximum number of electrons that can be accommodated in the first orbit of an atom is equal to 2. That might be any atom. In K shell, that is in the first shell, any atom can accommodate only 2 electrons. The first shell, the shell which is nearest to the nucleus of an atom, can accommodate maximum of 2 electrons. Okay, if there are more the electrons, then what happens? First electrons in that orbit will be filled, remaining electrons will occupy the higher energy levels. Okay, if you see second shell, the maximum number of electrons that can be accommodated in the second shell, that is L shell, is equal to 2n square. So here in the place of n, if you substitute 2, what do we get? 2 into 2 square, that is 8. So for any atom of an element or for any element, the maximum number of electrons that can be accommodated in the second shell is 8. Maximum 8 electrons can be accommodated in the second shell of any atom. If you see for third shell, that is M shell, 2 into 3 square, that is 18. So third shell maximum it can accommodate 18 electrons. And fourth shell, 32 electrons. In this way, the maximum number of electrons that can be accommodated in an orbit is given by the formula 2n square, where n represents number of the orbit. Okay. Next point. The outermost shell of any atom cannot have more than 8 electrons even if it has a capacity of holding more electrons. Yes, we are telling here, according to the formula 2n square, the maximum number of electrons is given. But for any element, the outermost shell can have maximum of 8 electrons. Okay, last shell of any atom will be having maximum of 8 electrons even though its capacity is more. Even though it can accommodate more number of electrons, last shell or outermost shell, the last shell of an atom is called outermost shell. So the outermost shell of any element can have maximum of 8 electrons only, even though its capacity is more. For example, M shell is the outermost shell of an atom. M shell means that is third shell. So it can accommodate a maximum of 8 electrons only. If it is outermost shell, it can accommodate only 8 electrons, although its capacity is a maximum of 18 electrons. So according to the formula 2n square, here we found the maximum number of electrons that can be accommodated in the third shell is equal to 2n square, that is 18 electrons. So the third shell or M shell can accommodate 18 electrons. You can know here that. But if it is the outermost shell of an atom, it is the last shell, then it will be having maximum of 8 electrons only. Okay, that's one condition they observed. Next point, an atom becomes stable if its outermost shell has 8 electrons. Okay, if any element, if it is having 8 electrons in its outermost shell, it is observed those atoms are being stable. They are being highly unreactive. If it has only one shell, then it can contain 2 electrons. So if it is having only one shell, then if it is having 2 electrons, then those elements are being stable. If it has more than one shell, then if there are 8 electrons in its valence shell or last shell, then that atom is observed to be more stable. It is having least reactivity. So the penultimate shell can accommodate a maximum of 18 electrons. What is here penultimate shell? We are telling last shell is called outermost shell. Outermost shell means last shell of an atom, which is being outermost. So last shell of an atom is called outermost shell. The next to the outermost shell, that is called last but one. The last but one shell of an atom is called penultimate shell. So the penultimate shell of an atom can accommodate maximum of 18 electrons, even though its capacity might be more. Okay. Electrons do not enter into a new shell before the inner shell is completely filled. Yes, it is one more point to be observed while understanding the electron configurations. So first, lower energy levels will be completely filled with electrons. Then only electrons enters into higher energy levels. So by keeping these all points in mind, we can write the electronic configurations of the elements. We can understand easily the electronic configurations of elements. Significance of electronic configuration. We're telling what do we understand from these electronic configurations. The electronic configuration of an atom helps in predicting the chemical behavior of an element. Yes, how reactive an element, how stable an element, how it participates in the chemical reactions. These all behaviors of elements can be predicted by using the electronic configuration of that element. So by studying the electronic configuration of element, we can predict the nature or behavior of an element. For suppose if an atom of element has completely filled outermost shell. Completely filled in the sense outermost shell can accommodate maximum of 8 electrons. So if an atom of an element has 8 electrons in its outermost shell, then the element will be unreactive or will be more stable. This configuration where there are 8 electrons in its outermost shell is called octet configuration. Octa means 8. Octet configuration means element configuration in which there are 8 electrons in the outermost shell. That is called octet configuration. If the outermost shell is K shell, if that means if the outermost shell is first shell itself, if it has only one shell, if it is filled with the 2 electrons, then it is called duplet configuration. So if an element is having only one shell and if it is completely filled with 2 electrons, then that configuration is said to be duplet configuration. If an element is having more than one shell, then if that element is having 8 electrons in its outermost shell, then that is called octet configuration. Okay? When the atom of an element has less than 8 electrons in its outermost shell, then element will be reactive or unstable. So in these two cases, if element is having duplet configuration or octet configuration, elements are observed with more stability or least reactivity. They do not participate in the chemical bonds. They do not participate in the combining. The other elements which are not having 8 electrons in their outermost shell, means the elements with less than 8 electrons in the outermost shell, will be more reactive. They will be highly unstable. Okay, these elements will participate in the bond formation. Next, valence electrons and the valency of the elements. First, let us say about valence electrons means what? The electrons present in the outermost shell of an atom are called valence electrons. So, an electron may have more number of orbits. The electrons present in the last orbit or valence orbit of an atom is called valence electrons. Outermost orbit means the last orbit of an atom. So the electrons present in this last orbit of an atom are called valence electrons. This last shell is also called as valence shell. Thus the electrons present in that are called valence electrons. These valence electrons are responsible for the reactivity of an atom. Okay. For example, the number of valence electrons of sodium. What is atomic number of sodium? 11. So its configuration will be 2, 8, 1. In this, in the outermost shell of sodium, how many electrons are there? There is only one electron. So the number of valence electrons of sodium is said to be now 1. Let us see one more example. The number of valence electrons of fluorine is, what is atomic number of fluorine? We know as it is 9. So if you write the electron configuration, we get it as 2, 7. Now for fluorine, the last shell or valence shell is second one now. In second shell, how many electrons are there? There are 7 electrons. So number of valence electrons for fluorine is 7. Okay, the electrons present in the last shell or outermost shell, or which is also called as valence shell, are called valence electrons. Okay, these valence electrons and this valence shell are responsible for the reactivity or non-reactivity of an element. If it has 8 electrons in the last shell, so that is called stable element. If it has less than 8 electrons, then it becomes an unstable element or reactive element. Next, about valency. Valency is different from valence electrons. Valence is defined as the combining capacity of an element is called its valency. So elements other than noble gases, that means elements which are having less than 8 electrons in the outermost shell. These elements are chemically reactive and stable because they do not have 8 electrons in their outermost shell. So these elements also will try to tend 8 electrons in their outermost shell. That is called reactivity of these elements. They tend to acquire stable outermost configuration of noble gases by gaining or losing or sharing electrons with other atoms. So the elements with outermost 8 electrons are stable elements or noble elements we call them. Like that, very few elements are existing. Most of the elements they do not have 8 electrons in the outermost shell. So these elements are said to be unstable elements. These elements also will try to get 8 electrons in the outermost shell so that they can become stable. So in this getting 8 electrons in the outermost shell, sometimes some elements they will gain electrons, some they lose electrons, and some other elements they will share electrons with other atoms. So that finally they will get 8 electrons in their outermost shell, so that they can become stable just like the noble gases. Okay, here, so in this way, the number of electrons gained, lost, or shared by the atoms is called its combining capacity. That we can define like this: the number of electrons gained, lost, or shared by an atom to complete its octet or duplet is called its valency. The valency of that element. Okay, we are telling elements which are not having 8 electrons in the outermost shell, they will try to either gain or lose or share electrons so that they will get octet configuration. Here, the number of electrons gained, lost, or shared by an atom to become stable is called its valency, which is also called as its combining capacity. Okay, next, elements with less than 4 electrons in their valence shell. So here we may get a doubt. We are telling some element they lose electrons, some element they will gain electrons, and some they share electrons. Which elements will lose electrons? And which element they may gain electrons? And which will share electrons? So for that it is also given. Elements with less than 4 electrons in their outermost shell or valence shell generally will lose electrons, and the elements which are having more than 4 electrons in their outermost shell will gain electrons to get the octet. So the element generally which are having nearly 4 electrons, they may share electrons. Okay, here we may get to some clarity. The atoms with less than 4 electrons in their outermost shell, generally they will lose those electrons so that it will get 8 electrons in the outermost shell from the last button shell. So they lose electrons. And atoms with more than 4 electrons in their outermost shell, they will get the remaining electrons from other atoms. They will gain electrons so that they can become stable. Okay. For example, let us say with some examples so that we can understand easily. If you see sodium, already you have seen its atomic number is 11 and its configuration will be 2, 8, 1. So how many electrons are there in the valence shell of sodium now? Valence shell means last shell. In the last shell, sodium has only 1 electron. So it has less than 4 electrons. Hence, this sodium will be ready to lose these electrons. Lose this 1 electron and become stable with 2, 8, 8 configuration. So by losing this, what we'll get? This will be the remaining configuration of sodium. So this is the nearest noble gas configuration, neon configuration. So as it is getting 8 electrons in outermost shell, it becomes stable. So like this, the atoms with less than 4 electrons in the outermost shell, they will lose them and they become stable. Thus, here the valency of sodium, how many electrons it is losing here? 1 electron. So the valency of sodium is said to be 1. Okay, let us see one more example. If we see oxygen, atomic number of oxygen is 8 and its configuration is 2, 6. So it has 6 electrons in its valence shell. Hence, it has, as it is having more than 4 electrons, it will gain the electrons. Hence, how many electrons are required for oxygen to become 8? 2 more electrons. Hence, it gains 2 electrons and becomes stable with 2, 8 configuration. So, after gaining 2 more electrons, its configuration becomes now 2, 8. like a noble gas. So it becomes stable. How many electrons it gained here? 2 electrons. Thus, the valency of oxygen is said to be 2. So in this way, number of electrons gained or lost by an element to become stable is called its a valency. Here, one point is very clear. Valency and valence electrons both are different. So for some elements, for metals generally, valence and valence electrons will be same. If we see for sodium, valency found here as 1. What is the number of valence electrons? It is also 1. But for non-metals generally, valence and valence electrons will be different. If we see for oxygen, what is the valence electrons for oxygen? 6. Because there are 6 electrons in its valence shell. So valence electrons is 6. But its valency we found it as 2. So for generally for metals, valency and valence electrons will be same. But for non-metals, valence and valence electrons will be different. Okay, I got it. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates on recorded videos.